the shape function, of course. Shape functions, of course. I screencast last time and showed you how to solve them, but we'll go ahead and do it again. This time in terms of the local coordinates. So the interpolation we're going to use is 1, x, y. A is x evaluated at the first node is going to be 0, y, 0. Okay, I'll just copy that. The second node is going to be what? X is A, y is 0. And the third node is what? Okay. And then the shape functions are going to be x dot inverse A. Okay. So there's our shape functions. Using those, we can define that B matrix. So we'll say B is equal to, and this is where I'll actually go ahead and show you the shorthand. If I say table I 1 to 3, okay, and I'm going to put something in right here, okay. Now, I don't know if you guys have discovered this, but if you go to palettes, basic math assistant, it brings up this little thing, a little palette that you can use to help you input your commands. And somewhere in here, under this tab, right here, okay, now we're only going to take the derivative once, but over here in this one you can see there's that little comma operator, which would be if you were taking like a second partial derivative. So it's not exactly the same notation I have up there, but it's pretty close. So what this means is we're going to take the partial derivative with respect to x of the ith shape function for I 1, 2, 3. Okay. And then we're going to do the same thing for y. And then we're not going to take a derivative in the last one. Okay, there's B. Now C is A11. There's no, for that Poisson equation I wrote up there, there's no A12, so it's 0, 0, 0, A22, 0, 0, 0, 0. Okay. So now we're ready to calculate the shape function, the element stiffness matrix. So we have to take two integrals, all right, and it's going to be B transpose dot C dot B X Y. Actually, want to go Y X. So in the Poisson equation I wrote right there, right? So C was defined for that longer equation. This is a special case of that longer equation we developed a finite element model for. But in this Poisson equation, those are 0. Okay. So can anybody tell me what the limits of integration are going to be for this triangle?
For y, it'll be from 0 to B, 0 to A.
That would be right if it was a rectangle.
It's from 0 to x.
In the y direction, we're going to integrate from 0 to that line, right, between 2 and 3. We're going to integrate from this 0 in the y direction. We're going to integrate from this line to that line. So we need the equation of that line. That's the limit of integration, which is minus b over a x plus b, right? mx plus b is just an equation of a line. The slope m is minus b over a. All right? and then the x direction, we're going to go from 0 to A. All right? So, everybody okay with that? Now, I want to point out something that, and I'll just, I'm going to copy all of this. And repaste it here. I want to point out that order matters. So if we order the element like this, the node numbers, okay, now our shape function is going to be different, right? The first node is not 0, 0, it's A0. The second node is 0, B, and the third node is 0, okay? Everything else will stay the same if we evaluate it. We get that. Now, let's see if I can get them on the same screen. I'll close this. So there's the first one, using the ordering where we started in the lower right hand corner. And here's the other one that we started with the one in the lower, I'm sorry, first one had lower left hand corner, this one had lower right hand corner. Well, they're not inverse, but the first, you basically swap the rows and columns of the numbers. So in the first one, what was 1 became 3. So we swapped the first row, first column, and so on. So if you knew one, you could determine the other ones not by having to recalculate everything, but by just swapping the rows and columns. All right? We can find the element force vector. It's really easy. You know, it's actually the same integral. We're going to integrate over the same. It's just going to be ln I. So that's the element force vector. Okay?